This looks simple enough, right? A pendulum swinging back and forth. But here's something strange. When physicists write down the equations of motion for such kind of oscillations, they do something that seems strange or rather wrong. They take sine theta and say, that's basically theta. But why is it true?
For that, let's take a look at sin x. Sin x is a curve that looks nothing like a simple polynomial. It waves and oscillates infinitely. But if we draw a straight line passing through the origin, it almost perfectly mimics the behavior of sin x near the origin. This is a very interesting phenomenon. Hence, in the pendulum equation, we can replace sin theta with theta for small swings, and suddenly this messy non-linear system becomes beautifully simple. Now, what if we take this idea one step further? Instead of using a straight line, we use cubics, polynomials of degree 3. Our approximations get even better, and as we keep adding higher and higher order terms, quartics, quintics, and beyond higher degree polynomials, the curve of our polynomial starts to merge with sin x itself.
Now, what if I told you that every smooth curve, every motion, every beam of light that you have ever seen could be described by nothing more than just polynomials? Basically, sum of integer powers of x. The same kind of equations that you have learned in your high school. This is what Taylor series makes possible. A bridge between the complex world and the clean precision of pure polynomials. Now, let's take a deep dive into the maths of approximations today.
This is the equation I was talking about, the Taylor series. It's basically an infinite sum of positive powers of x, each multiplied by just the right coefficient, where a is the point about which f is to be approximated. Simple on paper, but powerful enough to describe any smooth function. So let's unpack this. Let's explore the hows and the whys behind the Taylor series and see what makes it so special. Now that we know what Taylor series is, let's actually see one in action. We will take e raised to x, the exponential function. Let's expand e to the power x about a equal to 0. The calculation becomes really simple as the derivative of e raised to x is e raised to x itself. Using this, we can easily calculate the coefficients, and substituting the values of a and the coefficients, we get e raised to x equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, and so on. This expansion of e raised to x is also known as the Maclaurin series. At first, this looks like a random pile of terms, but each one is basically e raised to x saying, here's how I bend, twist, and curve near 0. Now let's examine the polynomial graphically. If we take the linear term, then we get a straight line that just touches the exponential curve near the origin. Adding the quadratic term x square by 2 factorial allows the polynomial to curve. Adding x cube by 3 factorial, the cubic term, brings the approximation even closer, almost indistinguishable from the true function around 0. Gradually, what begins as a simple polynomial evolves into a remarkably accurate local portrait of the exponential function itself. Here's a fun fact. Even modern calculators rely on polynomial approximations like this to compute values of powers of e.
So now that we know what Taylor series is and how to expand functions using it, let's see some real life applications of Taylor series.
Now let's get back to the pendulum. We know that the force of gravity acts downwards. Now if we split the force into its radial and tangential components, the radial component is nullified by the tension of the string. Thus the motion is caused due to the tangential component. So the net tangential force is equal to minus mg sine theta. Now according to Newton's second laws of motion, m times acceleration in tangential direction is equal to minus mg sine theta. Now the displacement in the tangential direction is basically the arc length, that is L theta. Differentiating it twice with respect to time, we get acceleration in tangential direction is L times the second derivative of theta. Now substituting L theta double dot into the equation, we get the equations of motion. But this is a non-linear differential equation which is very hard to solve exactly. Here's where the Taylor series of sine theta comes in clutch. We use sine theta equal to theta for small swings, and the messy non-linear differential equation becomes the clean SHM equation, which is way simpler to handle.
One of the other really important applications of Taylor series is in the optimization theory. Most of the optimization problems are minimizing or maximizing functions, say minimizing the heat evolved or maximizing the profits. But these functions are really complex and messy in real world situations. So what do? We take a polynomial model that approximates these functions locally, and we find the optimizer for this model, which is relatively much simpler to calculate as compared to the original function. This is what makes modern optimization from machine learning to engineering design computationally possible.
So now that we have seen how to get Taylor series expansion for any smooth curve and why expressing functions as an infinite series of polynomials is so incredibly useful, but there's still one big question left. Why does it work? How can an infinite sum of powers of x so precisely mimic any smooth function? In other words, what's the proof behind all of this? The next few minutes pack in a lot, so if it feels tense, try slowing it down or giving it another watch. Trust me, it's worth it. The Taylor series is built on a simple yet powerful property of the differentiable functions, the mean value theorem. It states that for any differentiable function over an interval AB, there exists at least one point C in that interval such that the slope of the tangent at that point equals the average rate of change between A and B. By rearranging this idea and expressing f of b minus f of a as the integral of derivative of f from a to b, this becomes the integral form of MVT, which forms the foundation for deriving the Taylor series. Now let us consider a function f of x and let f superscript n denote the nth derivative of f. Using MVT, we get that the integral of the nth derivative of f from a to x is fnc times x minus a for some c between a and x, and the direct integration gives us the n minus 1th derivative of f from a to x, that is fn minus 1x minus fn minus 1a. Equating the right hand sides of these two expressions gives us the key relationship that eventually leads to the Taylor series expansion. If we integrate this expression with respect to x From A to X, we see something interesting. A Taylor series like expression emerging on the left hand side. Integrating once more, we see the quadratic term pop up. As we continue this process, a clear pattern unfolds. After integrating n-1 times, we arrive at the general form, keeping fx on one side and rearranging the remaining terms, we get the Taylor series. The final term represents the error term after truncating the expansion at n terms. As n increases, this error term gradually becomes smaller and smaller. This proof not only shows why Taylor series expansion works, but also the simple condition that makes it happen, that is, fx must be infinitely differentiable near a.
Everything that we have discussed so far applies to functions of single variables. But the beauty of Taylor series is that this same mathematics can be expanded to multiple dimensions. I will explore this idea and its fascinating applications in the next part of the series. I hope that you have enjoyed the video. If you did, make sure to like and subscribe. If you have any questions or suggestions, make sure to drop them in the comment section below. I will love to hear them. You can also find my socials linked in the description. Thank you for watching. Bye.